Okay, well, we've made some alcohols using our substitution reactions and our addition reactions. So now we're going to actually look at what reactions alcohols can undergo. So we should remember that our alcohols are part of the alkanol homologous series or family of compounds. Okay, so they have a hydroxyl group where we have an oxygen covalently bonded to the hydrogen. Okay, this is important because we need to remember that this is then covalently bonded into the chain, and they behave differently than our OH minus hydroxide ions in solution. Okay, so this is an ion, so will form ionic bonds and react in different ways. The hydroxyl is not an ion, so it's not going to act as a base, and it has no acidic proton. So there's no acid-base characteristics to alcohols. We have another series of reactions that we look at. Of course, we have the combustion reactions, which they will undergo the same as alkanes and alkenes. The key is not to remember this, to make sure that you do remember this oxygen and hydrogen in the hydroxyl, which adds into your balancing of your oxygen, obviously, and your hydrogens for your water atom. So that's a common error to forget that, so make sure you don't. The main category of reactions that we're going to talk about with alcohols is oxidation. Now, we haven't done redox yet. You had a little bit of an introduction to it in year 10, but we haven't done redox chemistry yet. So the balancing of these equations we'll do once we've done redox chemistry, but at this stage we need to look at what happens to alcohols when we oxidize them. So they will undergo these reactions only in the presence of strong oxidants, and these are the two that you need to know. Your acidified potassium dichromate, so if you remember, dichromate was an anion of Cr2O7 2-. Potassium is a +1 cation, so potassium dichromate is K2Cr2O7. Okay, so this is the oxidizing agent, and it needs to be in the presence of H+. Okay, when we come to balancing the equations, you'll see why that is. And then the other one is acidified potassium manganate or potassium permanganate, which is KMNO4. And this again needs to be in the presence of H+. So we just do that with a /H+. Okay, so these are the two reagents that we use to do the oxidation. And what it will produce is a carboxylic acid, an aldehyde, or a ketone. And which one of these it produces depends on the reaction conditions, how long we heat it for, or the position of the alcohol in the chain. So let's have a look at those. When we oxidize a primary alcohol, so our primary alcohols, remembering we have R and then CH, OH, so our alcohol at the end of the chain. Okay, when we oxidize a primary alcohol, this is a two-step process. The first step, we will get the aldehyde, and then if we continue to oxidize the aldehyde product, we will eventually form the carboxylic acid. We do this using a piece of lab equipment called a condenser, which has water running in through the bottom, okay, out and up through the top. And what that does is it's on the outside of a tube and it causes a cold surface here. So when we boil something from a round bottom flask up into the condenser, the vapors will start to condense and then drip back down. Okay, so this way it means that the volatile products, which are our aldehydes and our carboxylic acids, don't escape, and then we can have the second step happen as well. So the first step, primary alcohol in the presence of our strong oxidizing agent will produce the aldehyde, and if we keep heating it in the presence of the oxidizing agent, we get the carboxylic acid. So if we have a look here at the pictures here, we can see that potassium permanganate starts out as an orange color. If we mix it with an alcohol such as ethanol, which is a primary alcohol, when this reaction occurs, the reagent will turn green, and this is because in here we have Cr3+. In here we have the Cr2O7, 2, which is orange, and the chromium here changes to Cr3+, which is green, in the reduction reaction. So the chromium gets reduced while the alcohol is being oxidized. So the formation of the aldehyde is this one here. So if we take ethanol, oxidize it, and we can use a square bracket to show oxidation, we'll get ethanol, and an equivalent of water. If we allow this to continue, the ethanol then will oxidize to form the carboxylic acid, ethanoic acid. For this one, we would need to isolate this from the reaction mixture as it forms if we don't want it to continue on to form the acid. And how we isolate that, if we wanted to form the aldehyde, we're looking at this one here. Okay, and we have this flask here which sits inside a warmed, more gentle warming, so usually inside a water bath, so it's gentle warming, and then what we do is we heat this, and this will then, the vapors will come up here, they will hit here, this has water in and water out, so they're going to condense, run down here and collect over here. Okay, so this is called distillation. Now, if we want to get the aldehyde product, we need to distill it off as it forms. If we don't want the aldehyde and we want the carboxylic acid product, we just use this apparatus here where we're going to have our mixture of components in the bottom here, and then it's going to condense up and then drip back down in the one thing and not be distilled off, and from this we will get the carboxylic acid. So as I said, we can simply represent oxidation by using a square brackets around an O, and you'll see this used by the IB quite a lot. We must put the Cr2O7, 2- and H+ above the arrow because they specify our reaction conditions and then the product that we will form, in this case the carboxylic acid. So we would write reflux under here in order to show that we understand that we need to reflux it to get through to the carboxylic acid. As I said, when we do redox, we'll revisit these equations. If you're feeling pretty confident with oxidation and reduction, you can have a look at them. These are balanced complex redox equations, so a little bit harder than what you've seen in Year 10 before. So another way of looking at oxidation, okay, is that we remove hydrogen and add oxygen. So here we can see that the oxygen-hydrogen ratio in this mixture here is 1:6. The ethanol is 1:4, and then we go 1:2. So in each step we're actually removing some hydrogens or adding in oxygen for the oxidation process. And they are the old style definitions for oxidation and reduction, which we no longer adhere to. Again, just another way of showing you this, but you do need to make sure that if you are asked for the conditions, you need to specify that the oxidizing agent is acidified and heat, and then if you want the aldehyde, you're going to specify distillation, or reflux, you're going to get the carboxylic acid. Okay, so it's really important that you take good notes on what the conditions and the reagents are for these. For a secondary alcohol, okay, so we've talked about primary alcohols, aldehydes or carboxylic acids, so they will give us the functional groups that are on the end of the chain. For a secondary alcohol, we're in the middle of a chain. So when we pull this hydrogen off and form the double bond, we're going to form a ketone. There's nothing else we can form, so it's just that one, and we again use the same acidified potassium dichromate or permanganate solution. Again, representing with the square brackets O, showing the oxidation has occurred, this time having our CO in the middle of the chain, indicating that we have the ketone. Going back to looking at it as looking at hydrogens being removed, we can see that we've removed 2 hydrogens. We haven't added any oxygen this time, but we have gone from a hydrogen-oxygen ratio of 1:8 to 1:6. So because we've decreased the number of hydrogens, oxidation has occurred in this case. and then showing again if we have propane 2-ol, so our alcohol in the middle of the chain, oxidation, heat and reflux, we will form propanone and then get water as a byproduct. Again, just pointing out that we will start with the dichromate, which is orange, and then the reaction mixture here would turn to green, indicating the oxidation has occurred. So this color change will only occur if oxidation occurs. So in the case of tertiary alcohols, they aren't oxidized easily by either of the strong oxidizing agents that we've mentioned. So these won't actually undergo a reaction, so the reaction mixture will stay orange in this case. And this is what we have here. So 2-methylpropan-2-ol is a tertiary alcohol. We can try and oxidize this and heat it, but we'll see no reaction, which means that our dichromate will stay orange in color, indicating that we have a tertiary alcohol. And this is one way we can distinguish between tertiary alcohols and primary or secondary alcohols. Okay, so this is just summarizing those for the secondary and tertiary alcohols. Make sure that you have good copies of these reactions in your notes. So a primary alcohol can form an aldehyde and then go through to a carboxylic acid, and we'll have an orange-green color change. If we were using MnO4-, okay, in the presence of H+, this would go from purple to colorless. You may get some brown Mn2+, but not often. And then this one would also go from purple to colorless as the reaction progresses. And then here the tertiary alcohol will remain purple, okay, because no reaction is going to occur for that. And this is an indication of those reactions. So we can see that both of these have turned green, containing the primary and secondary alcohols, and our tertiary alcohol remains that orangey color. So the next up is esters, and we'll do that in another video.